Here we discuss about a project, high-performance CORDIC-based approximate Mac architecture for FPGA platforms. In this project, presents an efficient design methodology for arithmetic hardware used in digital signal processing, image processing, communication systems, and embedded platforms where multiply-accumulate operations play a vital role. Here, CORDIC-based Mac architectures are particularly attractive for FPGA implementations due to their shift and add computation mechanism. However, the overall performance of these architectures is highly dependent on the efficiency of the adder and subtraction units employed within the CORDIC iterations. Conventional full adder and full subtraction designs typically result in higher area utilization, increased power consumption, and longer propagation delays. Although several CORDIC-based and approximate Mac architectures have been reported in the literature, most existing approaches rely on traditional arithmetic circuits and do not fully exploit logic-level simplifications. To overcome this limitation, this work proposes the integration of XOR mux-based full adder and XOR mux-based full subtraction architectures within the CORDIC-based Mac structure. By replacing conventional arithmetic units with XOR mux-based logic, the proposed design achieves a significantly simplified hardware architecture without compromising functional correctness. The proposed CORDIC-based Mac architecture is modeled and simulated using ModelSim to validate correct operation, and synthesized using Xilinx tools to evaluate hardware performance. Synthesis results demonstrate notable reductions in area, power consumption, and propagation delay when compared to conventional CORDIC-based Mac designs. These results confirm that the proposed approach is highly suitable for low-power, high-speed FPGA-based digital systems. Now we can verify this paper. This paper is full design for Mac architecture. Here they developed 3 different Mac architecture: exact, proposed Mac 1, and proposed Mac 2. These all designed developed with both signed and unsigned configuration. Here we proposed with XOR mux full adder instead of conventional design, because conventional design have 5 number of logic gate, but XOR mux design will have 2 logic gate and 1 multiplexer. It will reduce logic size and delay and power consumption in Mac operation. Here, Figure 1 shows the exact top-level schematic of 8-bit Mac operation. Option A showing unsigned architecture, Option B showing signed architecture. Here, the inputs are first scaled using shift operations to ensure CORDIC convergence. The Z path generates control signals, while the XY path performs shift and add-based partial product accumulation across pipelined stages. Finally, the result is rescaled to obtain the Mac output. This next architecture of Mac 1 present in Figure 4. This figure shows the 8-bit CORDIC-based Mac 1 architecture for unsigned and signed operations. In Mac 1, the CORDIC core is used only for multiplication, with the accumulator input initialized to 0. The Z path generates control signals, while the XY path performs shift and add-based partial product accumulation across pipelined stages. Finally, the result is rescaled to add it to the accumulator to produce the Mac output. The next architecture, Figure 5, shows the proposed adaptive CORDIC-based Mac 2 architecture using an FSM and a logarithm-based LUT. A comparator determines the maximum operand magnitude, and the LUT computes the required bit width using a log2 function. Based on this value, the FSM dynamically controls the number of CORDIC stages and intermediate precision. This adaptive operation reduces unnecessary computation, improving accuracy and hardware efficiency. This work we have done in Verilog HDL and functional verification done in ModelSim and synthesize using Xilinx Vertex 5 FPGA. This is Verilog HDL code for signed MAC in exact method. And this is the simulation results. Here we shown the output in waveform pattern for understanding. Here, XS is multiplied into ZS and sum with YS, and final output shown with YM. Here, XS and YS we given in constant input, and ZS only we vary and test the gradual outputs. This work we also checked with error terms calculation with using MED, NMED, MRED, and error rate. And this is the coding for unsigned CORDIC-based MAC unit. And this simulation results showing the operation of unsigned MAC unit. And next one is MAC 1. It's also designed with both signed and unsigned method. And this is the simulation results for signed output. And this is the simulation results for unsigned output. And next one is MAC 2. It's additionally have adaptive control block. And this is the top module coding for this MAC 2. And this is simulation result for signed MAC 2. And this is simulation result for unsigned MAC 2. And finally, this work we synthesize in Xilinx Vertex 5 FPGA. Here we analysis LUT, slice register, occupied slice register, IOB, delay in synthesize report, and power. And this is the RTL schematic for MAC 2 signed operation. And this is synthesizing results for MAC 2 unsigned. And this is the RTL schematic for MAC 2 unsigned operation. And this all parameters we updated in comparisons document. And this one is signed CORDIC MAC comparisons. And this one is unsigned CORDIC MAC comparison. And this one is error analysis difference of this MAC operations. And we written an abstract document for this work, title, base paper abstract. Objective of this work, proposed title and proposed abstract, related notes. Finally, literature survey and references. Thank you.
Are you planning to publish your next innovative research in IEEE Transactions on VLSI 2025? Welcome to NXFE Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At NXFE, we provide novelty-based VLSI projects carefully aligned with IEEE Transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation recorded video explanations on your system. IEEE guidance for paper writing and journal publication, affordable project packages with ongoing support, customization to match your research needs, early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.